Hello students, and welcome. Today we're going to tackle a really important topic in organic chemistry, the different methods we use to prepare haloalkanes.
We see these PVC pipes everywhere in our homes, right? They're used for plumbing, for all sorts of things. But have you ever stopped to think, how are they actually manufactured on such a massive scale? Well, that whole process starts with one specific kind of molecule.
And that molecule is the haloalkane. So why is it so important for us to learn how to prepare them? Because in chemistry, if you want to make something useful, you first need to be able to make your starting materials properly. This idea is absolutely crucial not just for planning out synthesis reactions in your exams, but also for how huge industries work in the real world. Okay, so here's our game plan for today. We'll start with an overview called 3 routes, 1 destination. Then we'll explore each route one by one, the random attack, the focused addition, and the precise swap. After that, we'll discuss how to choose the right path, and finally, we'll wrap up with a summary of all the key takeaways. Let's begin. Right, so first things first, you need to understand that there's no single one-size-fits-all method for making a haloalkane. Chemists have figured out several different ways, and the method they choose really depends on the starting molecule they have. So what's the main idea here? At the most basic level, it's actually very simple. We take a hydrocarbon, like an alkane or an alkene, and our entire goal is to find a way to attach a halogen atom, like chlorine or bromine, onto its carbon structure. That's it. That's the destination we are trying to reach. Now, to make all of this really stick in your mind, let's think of it like a journey. We have to reach our destination, which is the haloalkane, and we have 3 main roads we can take. The first one is the long road, which is free radical substitution. The second is a detour, using addition to alkenes. And the third is the direct road, which is substitution from alcohols. Each road is very different. Okay, let's hit the road. We'll start with our first path. This is the long and, pretty random road of free radical substitution. We use this method when our starting point is a simple, stable alkane.
So, what's the plan here? We take a very stable alkane, which doesn't really like to react, and we mix it with a halogen like bromine. Now, on its own, nothing happens. We need a trigger, and that trigger is UV light. We shine UV light on the mixture, and that energy kickstarts a chain reaction, which basically forces a hydrogen atom on the alkane to be replaced by a halogen atom.
Imagine you are in the lab right now. You take some colorless hexane, you add some red-brown bromine, and then you switch on the UV lamp. What do you see? Slowly, that red-brown color starts to fade away. This tells you a reaction is happening. But here's the most important part. This reaction is not very smart. It attacks the hexane molecule randomly, so you don't get one clean product. Instead, you get a messy mixture of things like 1 bromohexane, 2 bromohexane, and so on. It lacks control. So that lack of control is a big problem, right? And that's exactly why we need a better way. This brings us to route 2, a much more focused path, addition to alkenes. Think of this as a smart detour we can take if our starting material is an alkene. Now, here's the big change. No UV light needed. Why? Because the double bond in an alkene is already a hotspot for reactions. It's reactive and ready to go. So we simply introduce the halogen, and it adds itself right across that double bond, breaking it, and forming our new haloalkane. And the difference in the lab is just wow. If you bubble some colorless 1-butene gas through that same red-brown bromine water at room temperature with no special lights, the color disappears immediately. Instantly. And the best part, you get just one single predictable product, 1,2-dibromobutane. This reaction is fast, and it is very, very selective. All right, let's move on to our final and most precise method. We called this one the direct road for a reason. This method, substitution from alcohols, is all about surgical precision. This time, we start with an alcohol, which has that familiar OH group. And here, we use a special tool, a specific reagent like PCl3. Think of this reagent as a specialized key. Its only job is to go to the OH group, remove it cleanly, and put a chlorine atom exactly in its place. The beauty of this method is its control. I want you to remember this line. Only the OH is replaced, other CH bonds remain untouched. See? It's completely targeted. It doesn't touch any other part of the molecule. This is the complete opposite of that random attack we saw in the first method.
Okay, so we've seen 3 different routes: a random one, a focus one, and a precise one. So how does a chemist, whether in a lab or in a huge factory, decide which path to take? The entire decision boils down to one very important word: selectivity.
This table puts everything side by side perfectly. Just look. If you start with an alkane, you're pretty much stuck with the free radical method. You need UV light, and you have to accept that you'll get a messy mixture because of low selectivity. But if you're able to start with an alkene or an alcohol, you can use these much better methods, which give you high selectivity and one clean, predictable product.
Now, this brings us to a common trap that many students fall into. You might look at the free radical method and think, oh, that seems simple enough. But in the real world of chemistry and actual synthesis, it is almost never used. Why? Because it's messy and non-selective. Creating a mixture of products that you then have to spend time and money separating it's a very inefficient way to do chemistry. And let's come full circle, back to those PVC pipes we talked about at the beginning. To make the starting material for PVC, which is vinyl chloride, industry needs a process that is clean, efficient, and gives them exactly what they want every single time. They simply cannot afford to create a random, wasteful mixture. And that's why they prefer clean, selective methods like addition to alkenes.
All right, let's take a deep breath and summarize everything we have learned. These are the key points you absolutely need to remember for a solid understanding of this topic.
So, here's the main takeaway. There are 3 main routes to make haloalkanes, and your choice depends on your starting material. Free radical substitution is random and messy. Addition to alkenes is fast and specifically targets the double bond. And substitution from alcohols is a precise swap of just the OH group. And above all, always remember, in chemical synthesis, control and selectivity are what matter most.
And one last piece of advice from me for your exam preparation. Please, don't try to memorize every single detail. Just focus on the core idea of each of the 3 routes. Keep that mental picture of the long road, the detour, and the direct road in your mind, and know one clear example for each. If you do that, I promise you this topic will feel so much lighter and easier to handle. I hope this was helpful for you.